Welcome back to After Hours Engineering. In this episode, we're going to hit the ground running, making our first simulation of a key component of the processor, the register. As a side note, I'm going to assume that you have a little bit of exposure to Verilog, but not a whole lot. Having said that, let's keep our code structure fairly simplistic in order to keep the topic front and center on the processor and everything else in the background, or at least as much as we can. So let's start by writing our very first Verilog code, the register module. I've created a project folder here called Processor. I'm going to create a simulation folder, a synthesis folder for any of the targets, a module folder to hold all of our components in, and then a ROMs folder that the processor will eventually handle with. So let's create our first module, and I'm going to magically drag my module right over here. So I've created our modules folder, and I have our first module in it. This is Verilog code. I've called it register, and this is kind of basic Verilog. You can get quite extensive with adding in a lot of other features, scripts, macros, but I'm not going to really do that in this project. To try to keep us focused on the processor and high-level Verilog code. For me, I like to use the default net type to help reduce typos and other kinds of errors that can creep up. I have a default parameter, or I have a parameter defined here, which we will eventually override when we get around to it. I also like explicitly stating the logic types on separate lines, so there you go. And we have our output of our register right here. This is Verilog for defining an array of bits, so it'll default to 8 bits. So here is the main portion. This is a behavioral block. It's an always statement, and it is sensitive to the negative edge of the clock. In our processor, we will do two things. It's like a tick-tock. The rising edge of the clock will be to configure things, and the negative edge of the clock will be to do things. It's the action portion of our cycle, and I'll explain this later in some other diagrams when we get to the processor level. So in this case, our register, if the reset is active low, then we literally drive the outputs to 0. This is Verilog bit replicator. And so I'm creating whatever the parameter is defined to. Otherwise, if the load is low, we copy the data in to the data out. Now, this is an artifact of Visual Studio because of the font that I'm using, but in reality, it's actually, if I can get it without, yeah, see, it's trying to, there it is. It's more like that, and I really should change the font so you can see the proper Verilog tag, but this is really the less than equal sign, or the non-blocking feature of Verilog. Otherwise, if it's not reset or load, then the register maintains its value. And that's it. This is a fairly run-of-the-mill module. It's fairly basic. We have a clock input, reset, load, and then data in to be stored or data out to be read from. That's the register module. Next is the test bench, but before we cover it, let's take a look at the makefile that will drive the toolchain. For this processor, we're going to have a simulation directory, and underneath that will be all the simulations we'll do for each one of the modules or components of the processor. In this case, we want to simulate the register or test it with a test bench, so I'm going to drag over here a simulation folder, and underneath that is our first test bench, or our first simulation, the register. And here is the makefile. Now this is a pretty basic makefile here. It has a test bench defined up top. I like to put things into variables. We have our submodule, which is nothing more than the actual Verilog module that we created previously. The modules is all of them. And this is what's important, is our tool chains. For the simulation, we need the Yosys toolchain, and we need the Verilog toolchain. We're going to output it to some sort of RAM disk here. So let's take a look at this section of code, which is right over here. This is our module that we wrote, and soon our test bench. This is iVerilog, which is right here. This is the compiler. So it'll take both our module and a library of other modules and combine them to generate a netlist output. From there, it gets routed into the VPP, which is the actual simulator. From there, once the simulator has finished, it outputs a VCD file that GTK Wave can then read, and that's this final line right here. Now we have a basic makefile that will drive our workflow. Let's take a look at a simple, non-comprehensive test bench. Test benches usually have some sort of time scale defined, maybe not, but I have one here at 1 nanoseconds per picosecond. There's sometimes a lot of macros defined. I have one here that's defining where the output of the simulator sends its data to. Then you define some sort of test bench module, and it can be named anything you want really, but I've noticed that a lot of test benches will use something like _TB. You'll have some parameters defined. You'll have all of the inputs and the outputs to your module defined, and then a clock if one is needed for the module you're testing. And then finally the device under test, which is, you guessed it, our register. Again, it takes inputs and some outputs. The name of this really doesn't matter unless you're going to reference some of the fields within the module. So then we come down to the initialize step. We initialize the clock so it starts off low, and then we set up a behavioral block or a simulation block that changes the clock every 100 units of time. And again, that 100 units is defined relative to this time scale. So this will be 100 nanoseconds. Then we come down here and we have another initialize statement, and this one is to kind of set up the output of the simulator and then to actually tell it to dump and save waveform data. Verilog has a bunch of commands in it that you can use, and they all typically start with the $, which we've just seen here with dump file. You can print things out. It recognizes standard file printf statement and some special ones like M to list the module. Then we set up some pre-initial states before the simulation either starts. So we tell the reset pin that it's going to be disabled. All the data coming into the register is going to be 0. So we've set that to its inactive state, which is high, and we set the low to its inactive state, which is here. Now the simulation actually begins with another always statement here. So we wait for the beginning of the first positive edge of the clock, and at that time we do our configuration, our setup. So in our processor, on the positive edge of the clock, we do things to set up for the negative edge of the clock where the action takes place. So in this case, I'm waiting for the positive edge of the clock in the simulator, and I'm going to enable or activate the reset. Now it won't do anything until we get to the negative edge of the clock. And then I have one wait statement here so that we can sample the data from the register. If you don't put this in here, you're trying to read right on the change of the clock, and you'll almost certainly get wrong data on the output. This will actually fail its assertion. And I just throw in markers to see what time things were happening. So here we are, we're on the negative edge of the clock. One time unit later, we read the output of the register, and we expect it to be 0 because we reset it. So hopefully this assertion comes out to be true. Then we wait for the next positive edge of the clock, and we disable the reset because we're not trying to reset it anymore. We create some arbitrary value for our register to load, and then we enable the load register. So what we've just done is we put the value A0 on the input, we've disabled the reset, we've activated the load, and we're going to now wait for the negative edge of the clock. And that's what we're doing here. Again, we're waiting for the negative edge, we give it 1 unit, and then we test our assertion. And again, this is not a complete test bench, not even close to testing it. And if you were to add in formal verification, it would be even larger. But I'm just keeping things simple. This is just a register, and we want to see if we can load and read from it. So the final thing I want to do is to make sure that we can always reset it if it happens to have a value in it. So again, we wait for the positive edge of the clock. We bring the reset low, and then we disable the loading because we don't care to load anything. Now in a full test bench, you really want to test all the combinations, like what is it like if you're enabling reset, but yet your load is low. And I'm not testing that combination. Finally, we wait for the negative edge, we wait again one time unit, and we make our assertion. And there's our test bench. Now we're ready to tackle the simulation using iVerilog and GTK Wave. We'll bring up a command prompt here. We'll switch into the directory where the make file is. We can see that we have our make file over here. Our register, we have our test bench, we're ready to go. So I'll type in make space sim, and it's going to run this make file here. So we're ready to go. So let's run it, and there you have it. Now I've already set up GTK Wave session, so let's pretend that this reset doesn't exist. So I'll delete that. And what we want to do is bring in and view different signals in the simulation. So in this case, if you'll notice over here to the left, we have all of these modules and things right here. This all comes from this one file right here, this cells_sim module. So you have to scroll all the way down to the bottom to actually see our test bench. And here are all the signals that we have defined in the test bench at the top. So if I come over here to the test bench, scroll up to the top, you'll see all the signals that I've defined. So if I come back over here, and I want the reset. So I'll bring that over here, and I like to color code things. My resets are usually red. We'll bring this test bench over here, and we'll look to see how close it matches the actual test bench that we've set up. So we'll start here. We know that on the first positive edge of the clock, the reset goes low. So here's the first positive edge of the clock, and guess what? Our reset has gone low. Exactly what we expect. Then we wait on the negative edge of the clock. We wait 1 unit, and then we make our assertion. Is the output of our registry actually 0? So here's the output of our register, and I'll highlight it so we can see it. And sure enough, on the falling edge of the clock, the output is 0. So if we come down here to our next positive edge of the clock, which is right here, we set the reset to 1, the data into a value, and the load is activated, or brought low in this case. So we look over here in our simulation at the positive edge of the clock. Sure enough, there's our data, 00A0. The load has gone high and the reset has gone high. Yep, that's what we expect. So now we wait for the negative edge of the clock, and we wait 1 unit, and we test our assertion to see if that's correct. So if we go to the negative edge of the clock, sure enough, the output is 00A0, and that's it. Our load is still low because we're on the negative edge of the clock. The reset is still inactive. So we'll wait to the next positive edge of the clock before we configure for the next edge of the clock. So let's look at that. So the next positive edge is right here. We're bringing the reset low because we want to reset, and we're disabling the load. Is that what's happened? Yep, there it went high and the reset went low. Then we wait for the negative edge of the clock. That's right here. We wait 1 time unit and we make our assertion. Did it go? Was it reset? Yep, sure enough it was. They're all zeros. So this looks like a good simulation. It's doing what we expect it to be doing. And that's it for simulation. We have written a module and simulated it. With the simulation looking good, we're ready for the final step of the workflow, synthesis. And this is where the hardware comes in. But first, we need to create a few files to drive that workflow. In the upper left here is our Verilog code. It's where we will insert our synthesis code. Over to the right is our small microcontroller program for ESP32 that generates just 3 signals, a clock, the reset, and a load. To the lower left is the terminals for building and uploading to the FPGA, and one for running that microcontroller code. In the lower right is the actual hardware itself. Here we have the microcontroller, the ESP32 microcontroller. It sends its signals over to the FPGA, and the FPGA outputs its information over here on these LEDs. These white LEDs are the output of the registry. These two are the pattern indicators that I'll show in a minute. And this last signal is a clock that I use to indicate that the FPGA is up and running and has been programmed. So let's drag over our synthesis code into our project here. And in it we have a subfolder for register with 3 files. Let's take a look at the top file first. Most, or if not all, Verilog code that you are going to synthesize will have at least one top module defined. And it almost always defines your pins to the outside world. And here are all the pins that I'm either using or turning off. These pins are defined in a pin constraint file, which we have here. And this I downloaded from the Tiny FPGA website. And then you go through and you turn on all the pins that you want to use. So we'll go back here. In this case, there's a set of default or standard pin configurations that you would use with the FPGA. When we get to the Black Ice MX, it will have a different arrangement than what you're seeing here. So we have a bunch of outputs for the white LEDs that we showed earlier, 2 pattern pins. I disable or turn off the other pins so that they're not left floating. The LEDs will sit there and kind of look relatively dim. They'll be half on and half off. And then finally our input pins, our clock, reset, and load. And then the pulsing green light indicator to help me know that the FPGA is up and running. So we come down here, we define a couple of local parameters. I'm defining a data width for my register to be 8 bits. I want that little green LED to blink at 4 Hertz. I've got some more macros defined here so that you don't have to remember the pin numbers. I define a registry to hold the output, one for the input that we'll be manipulating with this pin pattern here. And then this is typical FPGA code for writing a clock and then subdividing it for a specific frequency that we want here. And here is the actual module that will load onto the FPGA relative to the top module. And of course we have our clock, reset, load, and the data in and the data out. This is the main portion of the code where we have an initial block. Not all things in an initial block will be honored by the synthesis, but some will. The pattern here is being set up to start at 0 and the data in is starting at all ones. And here is our first large behavioral block. Again, in my processor, all the components will do their work on the negative edge of the clock, but on the positive edge of the clock is where we set up for the next edge. And so, on the rising edge of our load signal, we will change our pattern and then update it to move forward. I could do a count of 1 here if I wanted to, but it's just more obvious if I actually set the bit patterns. So every time I toggle my load from low to high, it's going to update the pattern and change it. And we'll see that in the lights when we look at the hardware. Finally, we need to route everything to the pins themselves, at least all the outputs. Here's all the white pins, the green and the red for the pattern, and I make sure that I've set all these other pins to low so that they're not floating. And of course the last one is that green pulsing pin. This is our synthesis module. And now what we need to do is compile it and upload it. So let's take a look at the make file. Here's our top module again, and we have the one module that we'll be uploading along with the top module. We have a couple of defines here for where the output's going to a RAM disk. The tool chains that we have, don't need that. We have the ICE40 tool chain, the Yosys tool chain, and then a command that the Yosys toolchain understands. This command right here is literally being sent to Yosys, and Yosys will break it apart, and the very first thing it wants to see is what your target is. And this is specifying an internal script, and we could take a look at it. It's just a text file that lists a lot of steps that Yosys will go through in reducing logic in your circuits. And that's what this script is actually doing here. Of course, we really need to define the actual device where it's located. For the Tiny, it appears here. We also have supply the pin constraint file to the builder. So here's our first target. We activate the Yosys command. We pass it the command, some outputs to deferring some warnings and stuff, and then what we're actually going to feed to the builder. We also have the next stage is perform routing, and for that we need the next PNR, the newer version of the place and route tool. We tell it what chipsets we're using, some packaging constraints, outputs for logs, where some input and output files are going to, and then finally we're ready to upload it if, of course, the build and the route succeeded. Your route will typically fail things like combinatorial loops, and we'll cover that later on in the series. Finally, we're ready to upload. To do the actual upload, you have to take the hardware file that's generated and pack it all up into a bin file. That bin file can then be given to whatever your product is. In this case, the product is the tiny FPGA. So it comes with its own little program to take bit streams and load them up into the FPGA. That's it for our makefile. It's really not that complicated or big. Now that we have our synthesis workflow set up, we are ready to actually synthesize, upload, and control our register in the actual hardware. Okay, to synthesize, we're going to run our makefile and do a build on this top level module here. So we're going to run the build commands. So we do make space build, and there we have it. We've now synthesized our module. The next thing to do is go through the routing step. So I'll do a make route, and we now have an ASC file that is ready to be packed up into a bit stream. So we're going to run the upload command. Before we run the upload command, we need to make sure that our hardware is set up and ready to load. And this is the FPGA right here, and there's a little button on the Tiny that you push prior to doing your upload. This configures the FPGA for booting, basically. So I'll put my finger on here, I'll hit the boot button, do an upload. You can see down here we are uploading the bit stream, and there, it's done. Our FPGA has been programmed and we're ready to start testing out the registry. So let's start by resetting the registry. So we come over here, and now we're going to connect with our ESP32 program via the monitor. So we connect, and there we go. Now if you notice, the lights here have come up in some random configuration, and that's because the initial statement in our Verilog doesn't really honor the initial statements when you're synthesizing. So you basically have to connect and disconnect a couple of times until you get it to come up correctly. See how it's there? Now see, it's come up correct. We know that the pattern is set to 0, 0. That's what the red and the green are. That's our pattern right there. So we'll do an S to load and then click the clock. And you'll notice that all of these LEDs came on, and that's not part of the 0, 0 pattern that we had over here. It's actually part of this pattern right here. So our data in started the pattern off at 1, 1. Not at 0, 0. So it didn't honor the initial begin in here. So having said that, we can now start marching through our patterns right here and seeing how it loads the register with different items in it. So we'll take our load high. You can see that it's changed patterns to the next pattern ready to go, but the pattern over on display is different. That's because what's being displayed is the negative edge of the clock. This is representing the positive edge of the clock. So now we do bring our clock low and toggle it, and you can see now that we're looking at the next pattern, the one that was loaded, but our bit pattern is ready for the next one. So we now bring it high, now bring it low, and you can see how we're one ahead of it. Low, high, low, high. So you can see how it's going through. Now let's execute the reset command to see if we can't reset the thing. So we'll bring our reset low. So we'll hit the A key and then we'll clock it. Ta-da! It cleared our register. So we brought the reset low, so we'll bring it high again and clocks it. Now you notice that when I brought the reset high and I hit the clock button, this pattern showed up in the registry. And that's because in our module, in our Verilog module, our data in still contains the data. We didn't reset our data in object, we reset the register itself. So when I brought the clock from low to high, the reset from low to high, the clock reloaded the data in value into the registry. So it looks like the registry is working. Ta-da! Success! We have finally synthesized our very first component of our processor, the register here. We've just covered the entire workflow that we'll use throughout the series, and it will serve us well. In the next episode, we begin working on the design of the instruction set architecture, the ISA. When designing processors, the ISA is almost always the first step of the process, and it is where we will begin in the next episode. Till next time.